All right. Hello, everyone. I'm Martin, and this is Aristotelis. Both of us are PhDs. So we're presenting our work on a large-scale test corpus for semantic table search. So we focus on tables because they are frequently used, can be used in any domain, and are arguably one of the most popular data models out there. So that is also the simple reason why table search is an important task. So there are generally two different variants of table search. One is by keyword search, where the user expresses information need through a set of keywords, and the other one is by example, where the user provides an example table which contains data of interest. So the latter is what's often used in the data discovery task, where the task is to either expand an initial table or to discover new tables. And the aim will then be to retrieve a larger set of tables because we are no longer restricted by this limitation from keyword search, where we can only find tables that contain keyword matches. So to perform a relevance-based search, we need some kind of semantic understanding of the query and the table. And that's where knowledge graphs, they come into play, because they will allow us to perform entity-centric similarity measurements. So moving back to the data sets and related work, so there are already plenty of large-scale test corpora or table corpora. So there are, for example, the Wiki tables, WDCN, and Git tables. They are large-scale, but they do not come with any queries or ground truth. On the other hand, there are NCCIR, or there is WTR and SEMsearch, which do have queries and ground truth, but they are rather small because they have been retrieved through human annotation. And also they have been constructed through a biased pooling mechanism because they have used BM25 keyword search to retrieve a small subset of tables that they will then use for the human annotation.
Thank you, Martin. I will now discuss how we construct and evaluate our semantic table search corpus. And to ensure we capture ample semantic information, we focused on tables that contain at least 10 unique DBpedia entities. Applying this filtering, we're left with about 240,000 tables for the 2013 data set, where about 30% of the cell values have an associated DBpedia entity. To construct the query corpus, we select one wiki table from each wiki page, and specifically we select the wiki table that has the largest number of entity mappings in a single row. Overall, this results in a query corpus of about 9,000 tables for the 2013 data set, with an average of about 65 ground truth relevant tables per query. So how exactly we construct this ground truth? Since we're dealing with many tables, we would like to automatically generate a ground truth relevance based on the metadata information. We construct the ground truth relevance of a query table in the wiki page by comparing that wiki page's categories and navigation links with all other wiki pages. To do this, we use Jacquard similarity. For example, here the Jacquard similarity using categories between the Boston Red Sox and the Boston Bruins would be 2/9. A similar process can be applied when looking at navigation links. So in this manner, we can construct a ground truth as a set of relevance rankings for a given query table. We also evaluated the trustworthiness of our automatically generated ground truth using expert users and found good agreement between the user annotations and the generated ground truth. We evaluate the query by example corpus across various baselines. The first baseline we used is BM25, which is a well-known keyword-based approach. And our second and third baselines utilize semantic information from the entities in the query and target tables. In STST, we use the entity types from DBpedia and compute the average Jacquard similarity of the types across tuples between the queries and the target tables. In STSE, we create an embedding vector for each entity and compute the cosine similarity of the query entities with the candidate table. We experiment using 50 query tables and select 1 or 5 tuples from each, and evaluate the performance of the baselines. We look at the average recall at the top 100 and top 200. As seen in this figure, STST, STSE, and BM25 achieve roughly similar recall. However, the set of tables retrieved by STST and STSE are significantly disjoint from the ones from BM25. So this is not surprising, since BM25 is a keyword-based approach and will not be able to retrieve ground truth relevant tables that don't contain the keyword matches with a query. So STST and STSE can complement on tables retrieved by BM25. So in conclusion, we have shown that existing benchmarks for table search have been limited by the quality and the size of the tables and queries. Our constructed semantic table search datasets introduces a large-scale corpus with ground truth relevances generated beyond keyword matching, allowing for the exploration of semantic search techniques over our tables. As a resource, all our tables, queries, relevance assessments, as well as our user study and vector embeddings are available at the following GitHub link. Thank you.
Thank you.